I'm going to hand over to Bruce now, unless there are some more questions, who's of course going to give a plug for the labs at Macquarie. So Bruce I've known for a long time and is super duper expert in osmium, rhenium and osmium isotopes, and he's going to talk a little bit about the application of that in mineral exploration. So looking forward to this, Bruce.
Okay, thank you very much. After that introduction, I'd like to change pace perhaps quite a bit from the previous two talks, which were looking at how we can trace with stable isotopes and vector in particular, and jump into radiogenic land and go significantly up mass up the periodic table, and try and see how we can link the timing of ore deposits and the genesis with fingerprinting how some of the metals that we're interested in might have come from the mantle or been scavenged from the crust and sourced and transported into the configuration they are today. So for those of you who haven't dealt with this weird part of the periodic table before, rhenium and osmium are essentially platinum group elements, and they're both highly siderophile and chalcophile. So if there's iron around, they'll hang out with iron. If there's sulfide around, they'll hang out with sulfide. And basically, there's hardly any of them in general in the silicate Earth. Most of it's gone into the core very early in the planetary formation, and we're typically dealing with parts per trillion, 50 parts per trillion in the continental crust of rhenium and osmium. And we get really excited when we get in the mantle where we get a part per billion or 3. Those of you who have come across it probably know about osmium from its geochronology in ore deposit settings, particularly from the perspective of dating molybdenite, which is great because it partitions rhenium and not much osmium, so it ingrows really radiogenic osmium really quickly. We've also been able to date hydrocarbons and hydrocarbon migration and deposition ages of organic rich shales as well. So rest assured, I'll be talking about virtually none of those things today, just to change the pace a little bit, because I'd like to link how we can use that geochronology with metal sources, mantle crust interaction in the context of metallogenesis and metallogenic systems. So from an osmium point of view, slightly non-conventional, and how that might aid us in terms of understanding ore formation models and thinking about terrain selection. So although I said this one's actually a radioactive decay system, it has a half-life of 42 billion years. So that's 3 times the age of the universe. That's scarily close to a stable system that the guys were talking about before. There's actually 7 isotopes of osmium. 187 rhenium is the one that decays to 187 osmium down here, is the one we're interested in. There's actually a second decay scheme, which is platinum. 190 platinum decays to 186 osmium. But if we thought 3 times the age of the universe was a long time, then that decay scheme has a half-life of 450 billion years, and the parent isotope makes up virtually hardly any of the natural platinum. So we don't really use that routinely unless we're dealing with platinum ores or meteorites. But because both the parent and daughter are highly siderophile, that's great. But rhenium behaves differently to osmium as well. So they're both siderophile, they're both chalcophile, but they behave differently to each other. So this is really handy because rhenium's relatively compatible in silicate melts compared to osmium. So they're both compatible, but the rhenium will fractionate into the melts. And so over time, we see the continental crust has very high rhenium-osmium ratios, so it will ingrow to really radiogenic osmium isotopic signatures, leaving behind a mantle which has low rhenium-osmium ratios and is relatively unradiogenic. And this behavior has given us the opportunity to generate model ages, just like for neodymium, where we can back calculate a sample to some point in time when it was last in equilibrium with the mantle. We tend to use chondritic values for the mantle on Earth, where we use both the parent and the daughter. But in the case of osmium, there's some examples where we've melted so effectively all of the rhenium has come out of the source rock. So the residue has been left behind with no rhenium. And over time, therefore, the residue hasn't increased in its rhenium-osmium ratio, in its 187, 188, or its osmium-osmium ratio. So we can calculate back in time, assuming no radiogenic ingrowth as well. And these are called rhenium depletion model ages, and they apply for only samples that, if we measure today, they have subchondritic ratios. Now, there's a lot of jargon thrown in there, but these are pretty handy tools sometimes. So I thought a good place to start was to have a look at how this combination of techniques perhaps gives us some clues for some of the world's biggest ore deposits. And this is good because it gets back to some of the comments that Ryan was making as well earlier on. If we look at Witwatersrand, there was basically a simple debate regarding whether the gold was purely placer and hence trital in origin, or whether it was hydrothermally introduced sometime after deposition and focused through the conglomerates which host the gold mineralization and reductively precipitated when it interacted with hydrocarbons, or some combination of both. And so here we are in the Vaal reefs in the central Rand, central and western Rand in particular. Deposition was in this period prior to 2.7 billion years, but after 3.1 billion years. What we did is we went in and got some samples that have been previously texturally characterized and analyzed whole rocks, but then rather painfully separated out sulfide fraction by hand picking and an organic fraction by hand picking, and measured the platinum group elements and the rhenium and osmium isotopes. Much to our surprise, and this is the refrain you hear over and over again when you're dealing with osmium, that was unexpected. We randomly hit, of course, one in each fraction, a nugget of something that was incredibly high in platinum group element concentrations as well as osmium isotopes. They were highly unradiogenic in osmium isotopes, and so they have these relatively flat compared to the rest rare earth patterns, platinum group element patterns. All of the other samples though, the whole rocks, the separated sulfides and the organic fractions are depleted in IPGEs. There's nothing magical about IPGEs. They're simply the ones that hang out next to iridium on these plots, so osmium, iridium, and to a lesser extent ruthenium, and are relatively enriched in platinum and palladium. Okay. Now, none of these systems, however you cut the cake, define lovely isochrons. So it's a classic isochron diagram, parent, daughter, daughter, daughter. But for reference, I put the perhaps 3.5 billion years, but critically the 2.7 billion year reference line. So if these things were going to define isotopic equilibrium with their source region, then they should be plotting on arrays to the left of the 2.7 billion year isochron reference line. Instead, all of them, including most of the whole rocks, much to our surprise, were plotting at younger apparent ages as they were. And these clearly reflect open system behaviour after sedimentation within the basin, which we know took place by 2.7 billion years. But these three little nuggets that we also hit as well were actually subchondritic in terms of their osmium. So we're able to calculate rhenium depletion ages for them. And that's their maximum ages, saying that at least 2.6 in one case, 3.1 and 3.2 billion years ago was the last time those things were in equilibrium with chondrite, and they haven't ingrown any more osmium since then. So they can only be older than those ages. So that's really interesting. Even though we've got open system young apparent ages for the fractionated portions, we've got these ancient detrital grains, and this overlaps ages from osmiridiums and some of the native gold, as well as some of the detrital zircon ages from within the basin. So if we've got detrital zircons, there's a peak of 3 to 3.1 billion years within the detritus within the basin. And then the osmiridiums and our TRD ages from these unexpected portions sit within this range of osmiridiums as well, and the native gold model ages. So the conclusion for Witwatersrand, in a really rough, broad brush approach, was that the mineralisation displays clear evidence for post-sedimentation mobilisation. And this homogenised the PGE patterns to being those IPGE depleted patterns, and opened the system for rhenium and osmium isotopes. Although I'm not going to stand hand on heart and say what the actual age is, somewhere in that period of 2.2 to 2.3 billion years would be the best bet. But our model ages tell us that these high PGE abundance phases were probably detrital, and they were coming from some sort of a granite greenstone terrain, which can source the mafic stuff for the osmiridiums and the zircons for the felsic stuff. And the Barberton belt, for example, would fit the bill there. And so in terms of model testing, I would say it's not purely placer and it's not purely hydrothermal. It's some sort of modified placer source of the mineralisation in its current form that we see within the Witwatersrand basin. Changing gears a little bit, we've heard a little bit about copper from Mount Isa. Well, a number of years back, I was lucky enough to be involved with some work with a PhD student at Monash University at that time. And she looked at the copper mineralisation at Mount Isa and a range of samples, 5 samples, including one from the alteration halo within the ore body. There's a cross-section here, geological map across, and compared also with some whole rock osmium analyses from the Eastern Creek volcanics, one of the potential sources of copper within the mineralized zone. And we even, crazily enough, tried to analyze the Sabella granite and a couple of the host Urquhart shale sediments as well, to try and see if we could fingerprint potential sources of osmium that ended up in the ore body. So 2 surprising results. First of all, the mineralization returned ages of around 1370 million years. You can play with the regressions, whether you include all 5 samples or 4, but it doesn't really change the story. They overlap each other, this 37 million years. And they have, the critical point here is, okay, the age is younger than the host rocks significantly. But they have quite radiogenic initial ratios too. Initial is where the isochron intersects the y-axis. And we can try and map that onto, well, what was the isotopic ratio of, say, our potential sources for copper available at the time? And these initial ratios overlap, particularly the Cromwell member of the Eastern Creek volcanics. The Pickwick member is a bit more radiogenic, it would appear. And they're definitely a lot less radiogenic than the Sabella batholith granite. And so that is unlikely to have been a source of copper or fluids for the mineralization at the time. In a geological sense, the closure temperature for osmium, we know, is actually very low. And so it's probably lower than whole rock strontium. So there's been a lot of really interesting argon work done in the late 90s, and even whole rock strontium isochron work, which has a cluster of ages in this period between 1350 to 1400 million years. And of course, the osmium sitting right on top of that. The isonorogeny was over well before 1500 million years. So the critical question is then, well, what was the temperature trajectory of the terrain, and how does that relate to that mineralized assemblage? So either the terrain maintained its heat, or it cooled and became hotter again. Clearly, we've got open system behavior in terms of osmium at 1370 million years. So either the mineralization took place then, or there was a thermal overprinting event which opened the mineralized system to osmium, or both. And I guess my prejudice or my preference would be that the mineralization actually took place then. And a potential, I mean, the copper could have come from any other source that had that isotopic ratio, but it looks like the Eastern Creek Volcanics is the most viable of the locally analyzed sources for copper if you wanted locally crustally derived copper in the system. Okay. And just an aside, if I get time at the end, we'll talk about improvements in analysis. There's a reason people don't go around analysing granites for osmium. It's because they don't have any in it. Out of dissolving about 20 grams of granite, we got a massive 10 picograms of osmium. So we're looking at 0.1 of a part per trillion osmium in your sample. So it's not very much. That's 100 parts per quadrillion. Finally, in this little romp of osmium in terms of terrains, I wanted to, buoyed as it were by the apparent stupidity of being able to analyse A-type granites or granites, we did refine our analytical techniques in the way that Brandon was describing, recognising if we want to actually expand this to understand other problems, can we actually have a look at other granites and other granite systems around? And A-type granites are very, very important magmatic systems in the Australian Proterozoic. Here in South Australia now on the Gawler Craton, there appears to be some sort of temporal link between IOCG mineralisation. Everyone loves Olympic Dam, but Moonta Wallaroo and Prominent Hill and Karapatina, these sort of things, and the Gawler Range volcanics and their intrusive equivalent, the Hildeber Suite granites. And in actual fact, some people have even argued that this A-type magmatism in reconstructed space corresponds to maybe a hotspot plume, albeit a felsic hotspot, which traversed in reconstructed space from the Gawler Craton through Curnamona up to Mount Isa. And associated with that were pulses of IOCG-related mineralisation. Believe that if you will. It begs the question, well, what role then might A-types play in potential mineralisation? So we set out to compare two types of A-types, obviously the Gawler Craton ones, and the late to post-orogenic A-types in the Adelaide Fold Belt, which are clearly associated with delamination of subcontinental lithospheric mantle and influx of asthenosphere at the end of orogenesis. So we predict if there is any mantle input into the A-types, two very different types of mantle playing the game. One, some sort of modified mantle plume, depending on your genetic model, and the other being moderately uncontaminated asthenosphere. Okay, and the question then is there any role for mantle in metallogenesis, of course? So first of all, to the Adelaide Fold Belt granites, again, I was very surprised. These were incredibly unradiogenic in terms of osmium, and they even went to subchondritic osmium isotopes. So if we look at this panel up here, this is the initial age-corrected osmium isotopic signature for the rocks in question. These are the Adelaide Fold Belt granites, and regardless of concentration, even at excruciatingly low concentrations out here, they show no signs of crustal contamination or modification. Instead, they look like they've just fractionated out of partial melts. This is a 10% partial melt of the DMM, and they've just fractionated straight out to form felsic rocks. They haven't interacted or mixed with anything, and hence they're very, very unradiogenic. And that's consistent, so they're directly derived from the asthenosphere with closed system fractionation. And that's consistent with hafnium isotopes in zircons, which have crystallized out of these granites as well, so that they were new material entering the crust post-orogenic thickening. What really surprised me was that the osmium isotopes in the Gawler Range volcanics and the Hildeber Suite were really, really radiogenic. Even when we age correct them, they're still incredibly radiogenic. And this panel B here is the Hildeber Suite and Gawler Range volcanics. If there was significant mantle osmium in these rocks, then we'd expect unradiogenic signatures through here. Instead, these things are looking more like the osmium budget within them is coming out of the continental crust of some sort. Of course, the Gawler Craton has a 3.1 gigayear nucleus available to contaminate these things. Now, remember, these things have virtually no osmium in them anyway. So you would not need to contaminate them with very much crust to bring you up to osmium isotopic signatures here, because all of the osmium in them would be coming out of the crust. But this was slightly counter to their hafnium isotopes, which again tend to be generally fairly juvenile in the zircons from these same samples. But we do know from whole rock neodymium isotopes in the Hildebrand suite that there's immense regionality, and some of the Hildebrand suite granites go as low or as crustal as -15 epsilon neodymium, where they've clearly ingested and inherited a lot of Archean components. So to my mind, this major mantle flare-up, where we've got a huge amount of magma entering the crust at the same time as IOCG mineralization on the Gawler Craton, but there's no clear mantle-derived osmium, at least, or siderophile or chalcophile element mineralization, leads to an interesting interplay in terms of questions for the ultimate source of these elements within the magmas associated with these Proterozoic IOCGs. So it's a very open question to my mind. So with one eye on the time, I'll wrap up by saying where next. All of these things were done with fairly conventional technology, which required significant amounts of osmium to get to be done after painstaking laboratory work. Brandon talked about the problem with how long these analyses take. Well, to analyze a single osmium sample will typically take you 3 weeks to a month or so to run a batch of samples. So what we're looking at is how to improve the precision. If we're going to invest that much time on getting the samples and dissolving them, can we get as much information? And so at Macquarie, we've got a new relationship with Thermo Scientific, where we're able to get massively higher precision analyses. So we're 2 to 3 orders of magnitude better analyses on a fraction of the osmium, about an order of magnitude less osmium than we used to get out of the dissolutions we used to do. And even better, we've cut our actual machine time down by about 1/4. So that, from an instrumentation point of view, the world's a beautiful place where we live now. But our chemistry and sample preparation, which is what Brandon was talking about for the copper and zinc isotopes, is where we need to work. If we can get around this, we can actually get into routine granite analysis and particularly silicate mineral analysis, which can allow us to trace and do geochronology and tracing on alteration and petrogenesis and skarn-related assemblages. And actually, I'll make this slide stack available at the back end of this. I've got extra slides which actually talk about some skarn and eclogite assemblages where we've done this, but I might leave it there.
Thanks, Bruce. No, that's great. Now, I was interested in your thoughts on the plume track up from South Australia into Queensland.
Well, as a co-author on that paper, I've got to back it to the hilt, don't I? Look, it's a really interesting model. I mean, the rate of progression is appropriate for what we think of plate velocities at the time. And the only problem is, why was the plume producing massive volumes of A-type felsic magma instead of large amounts of flood basalts? But the rhyolites in the Gawler Range volcanics have pigeonite in them. So some of these things were erupting at 1,050 degrees Celsius. This isn't your bulk standard rhyolite. So we've got a problem with the GRV and the Hildebrand suite anyway. It was a hot terrain. we need an anomalous mechanism. A plume is one way, particularly if it gets stuck under a slab, which pipettes loves, and modifies it. That may be one way of doing it. And then it slowly burns its way through, and then we're left with cooler things as we go up. So I'm comfortable,
well, I'm interested
but I'm
in
not
it because
sold.
there are some drilling results that came up with some quite unusual geochemistry and mineralogy, but they're quite a long ways undercover. Ken Collison has linked them up with the plume track, and I was wondering your thoughts on that.
Oh, okay. No, well, I'm not familiar with these results, so we can chat about that in virtual drinks.
Well, I think we should. We do have a question. Does Broken Hill join up with the plume model?
No, Broken Hill predates, we think, a little bit. And again, Broken Hill has its own combination of problems because it's severely metamorphosed and it looks more like SEDEX and slightly older and predated. Now, whether you want to link a thermal anomaly with a nearby plume track adding to the thermal gradient to enable deformation, but in terms of source of heat or metal for the primary mineralization, I don't consider it a part of that.
I was on mute.
All right.
Talking away. And you've got a thank you there as well. So that's good.